Okay, so here is a very typical second order systems, and so here we can arrange. And for our case, we like to plot is when we set s equal to j omega. Again, here we're looking, when we do the Bode plot, we introduce s equal to j omega. Okay, so that one we introduce here. So here a little bit more arrangement. So j omega squared plus 2 zeta omega n, j omega plus omega n squared. And for given this one, it's not easy to work with. So we try to rearrange. So for this case, I'm going to divide the numerator by omega n squared, denominator again by omega squared. Okay, so here in the next step, I simply divide both the sides by the numerator denominator by omega n squared. Okay, so under these situations, and probably you can use it in your mind, you can do something. And here, let me introduce one parameter, say u defined as omega divided by omega n. Okay, so in this way, here I can simplify these expressions. So numerator equal to omega divided by omega n squared. So that basically it simply is u squared. Okay. Oops. Sorry. A typo here. So this is omega n. Sorry, please edit out that one. Okay. So under this one, this numerator should become 1. Okay. And then in the denominators, every single term divided by omega n squared. So right now, let me write it down from the back side. So here, omega n squared divided by omega n squared, that is 1. Okay. Then the second one is 2 zeta. And second one is we have the complex conjugate. Okay. So here this j here and 2 zeta. Okay. And then omega n divided by omega n squared, leaving omega n in the denominators, multiply with omega, so basically there's a u here. You good? Okay. And for this one, and that is j squared equal to minus, okay, omega squared divided by omega n squared, so that is this one. So from here we can come up with a very simple form. The real part is 1 minus u squared plus j in major part 2 zeta u. Okay, so that is based upon which we're going to plot. And so this is gj omega. Okay, so the remaining this is gj omega. Okay, so the remaining we're going to calculate this term and calculate this term. So let me move to there. So we're going to calculate gj omega, the magnitude, and then we put into the decimal the log. Okay, so that is about the magnitude. And then the angle, the phase angle equal to gj omega. Okay. And so for this one, gj omega, we can further have the form, the gj omega basically is the angle of the numerators minus the angle of the denominators. Denominator is 1 minus u squared plus j 2 zeta mu. Okay. Again, the angle of the g equal to the angle of the numerator minus the angle of the denominators here. So I'm writing that into that one. Okay. And this one we can be further simplified. Basically, the angle of a positive, this one equal to 0 degrees. So this one is minus. Okay. This one, angle of this one basically is we can use arctangent of the imaginary part and divided by the real part. So that is this one. I'm going to use as follows. Okay, so here I try to tabulate. certain extreme typical numbers before we proceed. The first one, we want to see when u is very small, less than 1, we see what happened. How about this? Let me add it up one more here. Sorry. So this one basically equal to log, and this one will be equal to, again, the magnitude of these complex numbers equal to 1. The real part plus the imaginary part. See, okay? Again, the magnitude of this one, if you look at this one, this is a complex numbers here. So its magnitude applied to the whole thing. Applied to the whole thing basically is 1 applied to the denominator here, right? So the magnitude of the denominator, which is a complex number, that representing is the square root of the real part square plus the imaginary part square. So right here we write yes.
Where did the square, the second square, come from?
Oh, sorry, that's my mistake. Yeah, sorry. Thank you. Yeah. So here I write too fast, and it shouldn't have any square here. Okay. So here again, the log of the inverse number, that is can be minus. We can put into minus 20 log, and then that basically is square root of something there. Okay, and then let me take the square root out. So that is log and 1 minus u squared plus 2 zeta u squared. Like this. Okay. So this is the magnitude we base upon. This is the phase angle we base upon. And then here we can begin to write it up something. So when u is very small, then basically you look at here, the magnitude when u equal to small, basically that is minus 10 and log equal to 1. So that is equal to 0. Right? Okay. And for the phase, when u is become very small, and basically that is arctangent 0. Arctangent 0, basically that is 0 degrees. Okay. And then when so here you can how about this? When u become very large, so basically this is minus 10 and log. And when u become very large, then basically it's about u to the 4th power. Okay, so that basically is minus 40 log u. Okay. And for this one, when u become very large here, then basically that number is equal. When u become very large, basically that becomes, that approximate is arctangent, and it pretty much is minus u and 2 zeta, something like this one. Okay. For this one, when u become very large, they can approximate it like this. And basically this meaning the arctangent of a minus number, and that pretty much is 180 degrees. And then we look at the in between. So for example, u equal to 1. We see that u equal to 1 is a very special conditions. And for this case, we plug in u equal to 1 here, so that one is minus 10 log. And we plug into here, so that basically is 2 zeta u squared, that is minus 20 log 2 zeta. Okay. So again, when u equal to 1, this term disappears, and this one leading to here. And then here, from here to here, I simply plug in u equal to 1. Okay, so when u equal to 1, that means when omega equal to omega n, that means when omega equal to our operational frequency equal to our the natural frequencies. So which means omega equal to omega 1, that means omega equal to omega n. So that is at the resonant frequencies. Okay, so that means if the system is oscillating per the working frequency, if we set it up omega equal to omega n, then at the resonant frequencies we have such situations. The magnitude at the resonant frequencies, the magnitude simply is governed by the damping ratio. The smaller the damping ratio, then this magnitude will be bigger. Okay. And now for this case, that basically when u equal to 1, that is minus arctangent, and 0 and 2 zeta. Okay, so basically that is certain number divided by 0. That means from here you can see that is almost 90 degrees. Okay. So in the handout, I give to you, and you can use MATLAB as well. But in the handout, we have the curve. So say here we plot this is a log omega, and this is the magnitude, and say in dB. Okay, so that is the purpose of this magnitude. When omega equal to very 0, so say for example here the omega say equal to 10 to the minus 8 here. Okay, so omega equal to radian per second using this unit. For example, at the very small omega, for example like this one, and we can calculate its magnitude equal to 0. So here we can try to plot the curve. So the magnitude nearby the small omega region is pretty much 0 here. Okay. So when we approaching to say omega, so say certain minus 7, minus 6, minus 5, etc. Say here, I just make up one. So say here is omega n, and the natural frequencies. So that means when omega equal to omega n, so that is this situation. The magnitude is determined by this, by zeta. Zeta is our damping ratio. So from the curve you can see. For example, if the damping ratio is equal to 0.1, so from here that leading to this magnitude is about 18 or 19 decibels. Okay, so you can read from the curve. And when zeta equal to 0.1, the peak is about 18 or 19. You can read from there. Okay, and so then we're going down. And going down to certain transition, I don't care about this moment. When omega become very big, which means when u become very big, then the magnitude equal to minus 40 of the log. So that means when we go to very large, the slope equal to minus 40 decibel per decade. That means here the magnitude divided by this, the magnitude divided by the log of the omega is equal to minus 40. So here this one representing is the slope of the asymptotes when omega equal to big. So basically here you can approximate something like this one. Okay. So for the transition in between, if you like, you can add more point follow up and to help you to do the point tracking of the tracing of the point. Okay. Okay. So that means in the homework you will see I ask you for given certain specific problem. I ask you to calculate the magnitude of this G at omega equals to 0.1 and the magnitude of the G at omega equal to 1, etc. So basically, if necessary, you can keep writing, you can keep tabulate additional value of the U, specific value of the U, and then hopefully that can help you to say, okay, the magnitude is here, 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 then you can do the curve tracking. You good? Okay. So this is omega equal to 0.1, and for the second order system, it's very precise defined. For example, for omega equal to omega equal to 0.5. So let me equal to here. So omega equal to 0.5, something like this one. Sorry, the zeta equal to 0.5, something like this. Okay, and here it's been listed on the curve. When damping ratio is smaller than when damping ratio is smaller than 0.707, that is equal to 1 over square 2. The magnitude doesn't have the overpeak anymore. Okay, so that is this case. So that reason, if you look at additional curves and this curve here, if you look at that carefully, this is 0.7, damping ratio equal to 0.7, they don't have a peak. Okay. On the other side, how to apply this curve? For example, if I would say, hey, we have a curve something like this, say this number is equal to say 10 dB. I tell you, if this is a second order system, and this is a curve being identified by experiment, I need you to give me an approximation of the damping ratio equal to how much? Then simply you compare this curve to the graph I provided, and basically you compare the peak value here. So here, for example, is 10. You can approximate, say that value could be between zeta equal to, this one will be between the 0.1 and 0.2 in this range. Okay, so from there, then you can, using this formula, you can begin to plot the different curve for, say, for zeta equal to 0.11 and zeta equal to 0.12 and until zeta equal to 0.20. For each case, you plot a curve and then you compare the magnitude. Then from there, you should be able to approximate what is the zeta for this given curve. You know what I'm saying? Good? Okay. So that is the one. And for the base is pretty straightforward. And base basically is so that is the base. Okay, so 0 degrees and minus 90 and minus 180. So at a small region, at a small omega, that is pretty much 0 degrees. And at a larger omega, that is 180 degrees. And at the resonance frequencies here, and that is 90. So here you can do roughly and just do the curve fitting. Okay, something like this. Something like this. Schematically, this is a correct drawing. And again, if you like to be precise, you can add it one more. So say U equal to 0.1, U equal to 0.5, and then U equal to 2 and 3, etc. That means that you can have more points in between then to help you to trace for a bigger curve. You good? Okay. So coming back on Wednesday, we will have additional portions of the Bode plot. That means composite form of the functions. And then from there, and you should be ready for the home line. Okay, thank you.